Why, hello. I am coming to you from my at-home classroom, and we're going to go over some of the circular motion free body diagrams. So just a quick refresher. This is in the packet that you have, and I have asked you to start by looking at the Desmos cases 1 and 2. So if you haven't done that, go do that now and come back. Welcome back. So let's go ahead and draw the free body diagrams based on the forces that are acting. So when we are analyzing objects moving in circular motion, instead of X and Y axes, we'll have a radial axis and a tangential axis. Today, we're going to focus only on what's happening along the radial axis because that is the axis along which a centripetal force will act, where a centripetal force is changing the object's direction. So the first situation that we already did, but just to warm up, is a satellite going around the Earth. So how I like to start is by visualizing the center of the circular path. So for the satellite, that is the center of the Earth. Then we draw I don't like that. Then we draw a straight line from the center of the circle to the object. Now this is the radial axis, and it's going to rotate with the object. Something like that. Let's see. Oh, see, over the winter break, I let people play with my iPad. That was a mistake. All right, here we go. Okay, so that dotted line represents the radial axis, and it rotates with the satellite. So the gravitational force always pulls towards the center of an object. And so the gravitational force on the satellite due to the Earth pulls towards the center of the Earth. So from here, we're going to write our net force equations. Net force along the radial axis is ma as always, but this is specifically the radial acceleration. And in case we need it, radial acceleration is v squared over r, or centripetal acceleration. The second equation comes from our free body diagram. Inward forces are positive. Outward forces are negative. And so in this case, we only have an inward force. And so our net force equation that describes what's happening on the radial axis is net force equals Fg. Now, as always, we can set these equal. So MAR equals Fg. Okay, so that's the basics. And we're going to stop there because I'm not going to expand Fg into mg because g is not 9.8 for the satellite. So we're just going to stop there. Okay, so case 2, where we left off, was a car going around a circular track. Now for this car, it also has a gravitational force. It's straight down. And it has a normal force straight up. Neither of those provide centripetal forces, since neither of them have a component along the radial axis here. Only the static friction force has a radial component. I was just having a moment where I wasn't quite sure where I wanted to draw it, but this works. Okay. So the net force along the radial axis is only the static friction force. Now, if we are interested in, let's set this equal. Now, a lot of times, if we're trying to solve a problem about a car going on a turn, we're interested in a boundary, the maximum speed, the minimum radius, or the minimum coefficient of static friction. If any of those is what we're solving for, then instead of Fs, we would use Fs max. So of course, for a car on a flat surface, to figure out the normal force, we can look at what's happening on the vertical axis. So this is what's radial, vertical. It's not accelerating. Whoa. We have Fn up, and we have Fg down, or mg. And so from there, we could combine them and solve for whatever it is we're looking for as far as the speed, radius, or coefficient of friction. It's being loud, so I can put something quieter. Probably not. All right, let's keep going. So for the case 3 and 4. So what I'd like you to do is go back to the Desmos, try cases 3 and 4, and then come back. I know it stinks, but okay, we'll go back. So in case 3, oh, you didn't tell me my mouse. I hate when the mouse is in an annoying place. All right. So this is crazy, right? The gravitron's crazy. We'll talk a little bit about this ride in class, but for right now, when we are talking about the gravitron, it's a person in a vertical spinning cylinder, and the radial axis, is that horizontal? Okay, the radial axis looks like this. The normal force, which was, so it's the same 3 forces as for this car, but they rotate kind of. So Fg, of course, is still straight down, or mg. I'm going to switch to mg. The normal force now, instead of pointing up, is actually pointing towards the center. And the force that prevents the person from sliding down the wall is a static friction force that's equal in size to the weight. Oh. Normal force. Okay, this is now correct. So the normal force is the centripetal force, and the static friction force and the weight cancel out. So net force along the radial axis is MAR, which is mv squared over r equals Fn. So MAR equals Fn. Along the vertical axis, net force Y equals 0. We have static friction force up, and we have the weight force down. So 0 equals Fs minus mg. So yet again, when we are actually solving for something with this situation, chances are we're interested in a boundary where the people are about to start to slip down the wall. So that would happen if the V is minimum, if it's spinning too slowly, if mu is minimum, if it's too smooth, or if R is max, if it's too big. So in that case, this Fs here would become Fs max, which of course would become μsFn. All right, now we get into some roller coaster stuff. So when we look at case 4, we have a car going over top of a hill. Now this is a case where you could have my favorite, well, I don't know, as I get older, I don't know what my favorite is anymore, but one of my favorite things has been airtime, where you're going over the top of a hill in a roller coaster and you actually leave your seat because you're going so fast. Now, the reason you leave your seat is not because the road pushes you up, it's because basically you want to keep moving in a straight line. And so in this case, like a car, you'll see like in movies where cars actually leave the road, right? They go flying. It's not because the road pushes them up, it's because they're going so fast that they essentially become a projectile, and the curvature of that projectile motion is larger than the curvature of the hill that they're on. And so they just leave the hill. So this car is not doing that. It's not leaving the hill. It's just going fast and I feel a little bit like, woo, as they go over the top of it. So that star represents the center of the circular path. Wow, that was not great. There's my radial axis. So the weight is going to act, of course, straight towards the center of the earth. But what's strange here is that that normal force is small. The apparent weight is less than the actual weight. So this is a situation where we're going to bring that term apparent weight. And so here Fn is going to be less than mg. They're going to feel a little bit floaty. And one of the reasons I know, just like as far as like helping myself through it, how I know Fn will be less than mg is the net force has to be inward. We need a net inward force to have circular motion. And so mg must exceed Fn. That helps me think about how these forces relate to each other. Another thing that tends to freak people out a little bit about this is that since positive is inward, when we write our net force equations along the radial axis, we actually have mg is positive because that's inward. And then we have the normal force is negative because it's outward. And that's something that definitely takes a little bit of getting used to because we've done so many problems where the normal force is in the positive direction and the weight is in the negative direction. But here, those are switched because inward is positive. Okay, so we can set these equal. Now, one thing I want to say here is it might have freaked you out a little that I didn't draw any horizontal forces on the car. One reason why is that the idea here is that the speed of the car isn't changing. And remember, an object in motion will stay in motion. We don't need to have a force on this car horizontally in order for it to be moving horizontally. Also, I'm not really interested right now in talking about tangential acceleration, in other words, a changing speed. So it does nothing to do with what would be happening along the radial axis. So we're just going to worry only about radial forces right now. Okay, so that's one experience on a roller coaster or in a car, going over the top of a hill and kind of feeling floaty in your seat when Fn is less than mg. Another possibility, is case 5, but you haven't done the Desmos yet. So pause this, go do the Desmos, and I'll come back. I'll be here. Welcome back. Okay, so this might not look like something special, but actually riding through the bottom of the loop is where you're going to actually feel the greatest force on a roller coaster. And here's why. So the center of the circular path is here. The radial axis is here. Your weight, mg, is down. Now, the ground has two jobs. It has to support you, and it also has to accelerate you up that ramp. So this normal force here, or your apparent weight, is going to be greater than mg. And again, a couple different ways to come at why. One, net force must be inward. Rules are rules. In order for the net force to be inward, Fn must be greater than mg. But the real why is that the normal force here is accelerating you upward because you were just coming downward. This is just in a snapshot, right? This is not a stationary car. This car is moving to the right. An instant earlier, it was moving downward. And so the normal force has to take that downward motion and turn it into upward motion. And so it's going to have to exceed the weight and provide that change in direction upward. So when we write our net force equations here, net force is ma, and the net force is Fn minus mg. And so MAR equals Fn minus mg. This is actually the place in a roller coaster that you will feel the most crushed into your seat, where you're going to feel possibly the most likely to pass out or something, because this is where you're subjected to the highest accelerations and the highest normal forces usually, because you're going usually fastest here as well. This is why we don't see circular loops really on roller coasters. Usually, there's a beautiful word for it. I'm forgetting what it's called. I'll remember in class. But I'll save the stories for later because they're fun to talk about. Okay. Finally, last one we're going to do right now is case 6. So the same roller coaster, now it's at the top of the loop and it's not falling down. This is like the cup of water that we did on the platform. It is not falling down because it is moving. All right, so here's my radial axis again. Now, what's confusing about this one is the car is on the inside of the track. So besides mg pointing straight down, the normal force is pointing straight down as well. And so both of those forces are acting together to provide a centripetal force. They are both positive. So we have mg plus Fn here. Okay, so just a quick recap of the last couple cases. So when a car goes over the top of the hill, the normal force must be less than mg because we have to have a net inward force and the car is like trying to travel in a straight line. When the car goes past the bottom of a hill, then the normal force must be greater than the weight because the normal force has to provide that inward force and change the direction of the car. And then finally, when they have a roller coaster at the top of a loop, now all bets are off. The size of this normal force depends on how fast the car is going and how big the circle is and its mass. So Fn could be any value from 0 to who knows what. It just depends how big the speed is. So it could be smaller than the weight or larger than the weight or 0. So if one of the questions that comes up is what's the minimum speed to successfully navigate the loop? Without falling, without losing contact with the track. So if you're traveling at the absolute slowest speed that will successfully make it through the loop, then the normal force is going to be as small as possible. In fact, it will drop to 0, but only at the very top. And so as it crosses that top point, which is pictured here, it would only have a centripetal force equal to mg. And so that inward force would be entirely provided by the weight. And that would be how we could figure out the minimum speed of a car going through a loop. All right, looking forward to talking to you more about this stuff in class. Bye.